Corny chocolate, Snickers, and Hershey's all hide a different secret inside their chocolate. These brands never want to share how their product is truly put together, because what they do to provide millions with chocolate every day is extraordinary. In this video, we uncover how these three treats are shaped, coated, and wrapped before they become the snacks people reach for without thinking. Corny chocolate production begins with a hot binder syrup forming inside a heated mixing vessel. Sugar syrup, glucose syrup, honey-like syrup components, fat, cocoa ingredients, and flavoring are measured into the tank. The liquid warms as the agitator turns. At first, the mixture is thin and separate in places. As heat spreads through the vessel, the sugars dissolve, the fat disperses, and the binder becomes glossy and uniform. This binder is the part that turns loose grains into a bar. It must be sticky enough to hold cereal pieces together, but not so fluid that it runs away from the mixture. It also must cool into a chewy, stable structure. The tank controls temperature and mixing speed so the syrup stays pumpable without becoming too dark or too thick. Dry cereal ingredients are prepared on a separate line. Rolled oats, crisped rice, wheat flakes, corn flakes, puffed grains, and small cereal clusters can be combined depending on the specific bar formula. Each ingredient moves through its own feeder before joining the main dry blend. The dry ingredients pass through screens before mixing. Oversized clumps are removed. Fine dust and broken fragments can be reduced so the bar does not become powdery. The goal is a mixture with visible grain pieces and enough small particles to fill spaces between larger flakes. Chocolate chips or cocoa-flavored pieces may be added to the dry stream. These pieces must be cool and firm before they enter the mix. If they are too warm, they smear into the cereal instead of remaining as separate inclusions. The feeding system meters them gently so they do not break apart before forming. The cereal blend enters a large horizontal mixer. The paddles rotate slowly, lifting and folding the light grains without crushing them. The hot binder syrup is pumped in through several nozzles, spreading across the moving bed of cereal. The syrup lands as thin ribbons. The mixer turns the grains through the syrup again and again. Dry flakes become glossy. Puffed pieces catch the binder in their rough surfaces. Small grains settle into gaps between larger pieces. The mixture changes from loose cereal into a sticky, connected mass. The timing of this stage is critical. Too little mixing leaves dry pockets that fall apart later. Too much mixing breaks flakes and compresses the texture. The mixer must coat the grains evenly while preserving their shapes. Once the cereal mass reaches the right consistency, it discharges onto a forming conveyor. The mixture is warm, sticky, and uneven at first. It drops as a thick layer and passes beneath spreading rollers. Side guides contain the edges so the layer stays at the correct width. The forming section compresses the mass into a continuous slab. A first roller spreads it. A second roller levels it. A calibrated compression belt presses from above, while the conveyor supports it from below. The grains lock together as the binder fills the spaces between them. The slab thickness determines the final bar height. If the slab is too thin, the bar becomes brittle and flat. If it is too thick, the center may not cool evenly. The forming equipment holds the layer at a steady height across the entire width. The top surface is textured by the grains, but the slab must still be even enough for cutting and coating. The rollers do not grind the cereal smooth. They press it just enough to bind the structure while leaving visible oat flakes, puffed grains, and crisp pieces. The warm slab moves into a cooling tunnel. Cold air passes over the top and through the conveyor area. The binder begins to firm. The mass changes from soft and sticky to flexible and stable. It must cool enough to cut cleanly without cracking. Inside the slab, the syrup sets around the grains. Each piece becomes part of a larger network. The The bar texture depends on this balance. The binder stays chewy, while the cereal pieces remain crisp or lightly crunchy. After cooling, the slab reaches the cutting section. Long circular knives slice it lengthwise into continuous strips. The blades pass through grains and binder, leaving straight edges. The strips separate slightly as they move forward. A cross cutter then divides the strips into individual bar lengths. The blade moves in rhythm with the conveyor. Each downward cut creates another bar. The cut must be fast and clean, because slow pressure would drag the sticky binder and deform the edge. The separated bars now have their cereal structure, but the chocolate part still needs to be added. Chocolate coating is prepared in a separate system. Cocoa ingredients, sugar, milk powder, cocoa butter, or coating fats, and flavor components are mixed into a smooth chocolate mass. The mixture passes through refining equipment to reduce particle size and remove grittiness. The chocolate then moves through conching or intensive mixing. The mass becomes smoother and more fluid. Fat coats the dry particles. The chocolate develops the flow needed for coating the bar evenly. Before coating, the chocolate is tempered or conditioned depending on the coating type. Temperature is adjusted so the chocolate sets with the correct firmness and surface finish. The coating must remain liquid at the enrober but become solid quickly after cooling. Corny chocolate bars can be coated in several ways. Some versions receive chocolate on the bottom only. Others are dipped, striped, or fully enrobed. For a bottom-coated bar, the cereal bar travels across a chocolate bed or roller that applies a layer to the underside. The underside touches the liquid chocolate and picks up a smooth base layer. Excess coating is scraped or controlled by rollers so the layer is even. The chocolate base helps hold crumbs, adds flavor, and creates a clean surface against the wrapper. For a fully coated format, the bars enter an enrober. They ride on a wire mesh belt under a falling curtain of chocolate. The chocolate flows over the top, down the sides, and around the cut edges. A lower coating stream covers the underside through the mesh. Excess chocolate drains away and returns to the circulation tank. Air blowers remove extra coating from the top and sides. The airflow smooths the surface and controls thickness. The coating must cover the uneven cereal edges without becoming too heavy. For striped bars, the main chocolate layer sets slightly before thin nozzles apply lines across the top. The nozzles move, or the bars pass beneath them at a controlled speed, creating repeated chocolate stripes. These lines sit on the surface as a decorative and flavor layer. After coating, the bars enter a cooling tunnel. Chilled air flows around them while they move forward. The chocolate changes from liquid to solid. The surface firms first, then the full coating stabilizes. The cereal center remains intact inside the shell or beneath the base layer. Cooling must be gentle enough to avoid cracking, but strong enough to set the chocolate before wrapping. If the coating is still soft, it will smear on belts and film. If it is cooled too aggressively, the surface can lose its smooth finish. At the tunnel exit, the bars pass through inspection. Cameras check length, width, coating coverage, broken edges, exposed cereal patches, chocolate smears, and missing stripes. Metal detectors scan the product stream. Bars outside the programmed limits are rejected automatically. Accepted bars move into the wrapping section. Timing belts separate them into equal gaps. The bars align lengthwise, so each one enters the wrapper in the correct position. Printed film unwinds from a roll. Tension rollers keep the film smooth. Registration sensors read printed marks so the wrapper design lines up with the bar. The film folds around the product through a forming box. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back ends of each pack, sealing and cutting one wrapped bar from the continuous film. The wrapper protects the cereal texture from moisture and keeps the chocolate surface clean. It must sit close to the bar without crushing the grains or marking the coating. Wrapped bars pass through check weighers. A short bar, broken bar, or missing product produces a weight outside the target range. Vision systems inspect seal quality, film position, print alignment, and code placement. Defective packs are diverted from the line. A naked Snickers center enters the enrober with its layers exposed. The bottom layer is pale nougat. The top layer is caramel packed with roasted peanuts. The sides show the cut structure clearly, with soft nougat below and darker caramel above. It already has the shape of a bar, but it is not finished until chocolate surrounds every exposed surface. The center rides on a wire mesh belt. Ahead of it, tempered milk chocolate circulates through a coating system. A pump lifts the chocolate into an overhead trough. From there, it falls as a smooth curtain across the full width of the conveyor. The center passes through the curtain. Chocolate flows over the peanut caramel top first, then down the sides and across the cut ends. At the same time, a lower coating stream covers the underside through the open mesh belt. The bar becomes enclosed from all directions. Excess chocolate drains away through the belt and returns to the reservoir. Air blowers remove extra coating from the top and edges. The airflow smooths the surface and controls shell thickness. Too much chocolate would bury the shape. Too little would expose peanuts, nougat, or caramel. A short vibrating section helps the chocolate settle. Tiny air bubbles rise from the coating. The liquid shell rounds the corners and fills small uneven spaces around peanuts near the surface. The bar now looks finished, but the chocolate is still soft. Before this enrobing stage, the center is built as a wide layered slab. The nougat layer begins with a cooked sugar syrup. Sugar, glucose syrup, and water are measured into a cooker. Heat drives off moisture, making the syrup thicker and more concentrated. The syrup must reach the correct solids level because it controls the chew and stability of the nougat. In a separate mixer, an aerating base is prepared. A whipping ingredient is hydrated and beaten until it can hold fine air bubbles. The hot syrup streams into this foam while the mixer turns. The foam becomes stronger and heavier as the syrup blends through it. The mixture changes from light foam into dense confectionery nougat. It traps many small air cells, giving the layer a softer bite than caramel. Milk ingredients, fat, peanut flavor components, and other formula additions are folded in. The mixer works the mass until it becomes uniform. The nougat must be soft enough to bite through, but strong enough to support caramel and peanuts. If it is too weak, the bar compresses during cutting. If it is too dense, the center loses its light chew. The finished nougat leaves the mixer as a warm, elastic mass. It is deposited onto a forming belt. Rollers spread it into a continuous sheet. Side guides control width, and calibrated rollers set thickness. The surface becomes flat enough to receive the next layer. The nougat sheet enters a cooling section. Cool air firms its surface while the inside remains chewy. This prevents the caramel layer from sinking too deeply into it. The caramel layer is produced separately. Sugar, glucose syrup, milk ingredients, fat, and water enter heated kettles or continuous cookers. The mixture starts pale and fluid. As water evaporates, the liquid thickens, darkens, and becomes glossy. Agitators keep the mass moving so it cooks evenly. The caramel must have a stretchable texture. It needs to hold peanuts in place, but it also needs to pull, rather than snap when bitten. Cooking temperature, moisture level, and cooling temperature all control this behavior. Roasted peanuts are prepared on their own line before they reach the caramel. The peanuts pass through cleaning and sizing equipment. Screens remove small fragments and oversized pieces. Airflow pulls away skins and loose material. The accepted peanuts move into a roaster. Inside the roaster, hot air moves through the peanut bed. Moisture leaves the nuts. The texture becomes crisp. the peanuts develop the firmness needed to survive mixing and cutting without turning into powder. The roasted peanuts leave the heat and enter cooling. Air draws away heat quickly, stopping further roasting. After cooling, they pass through another screening stage. Broken pieces, skins, and undersized fragments are separated from the mainstream. The caramel and peanuts meet shortly before layering. Warm caramel flows through a mixing section, while peanuts are metered in at a controlled rate. The nuts become coated by caramel and spread throughout the mass. The mixture becomes thick, heavy, and textured. This peanut caramel mass is deposited across the cooled nougat sheet. A wide slot nozzle or depositor lays it down as a continuous band. Leveling equipment spreads it evenly from side to side. The peanuts must be distributed consistently so every cut bar contains the same type of layer. The two-layer slab now moves through a setting tunnel. Cool air firms the caramel enough for cutting. The slab remains flexible, but it can hold its shape under knives. The nougat, caramel, and peanuts bond into one continuous sheet. The slab reaches the slitting station. Long circular knives cut it lengthwise into narrow ropes. Each rope shows the same cross-section. The knives must pass through peanuts cleanly without dragging caramel down the sides. The ropes move apart slightly. A crosscutter then divides them into individual bar lengths. The blade moves in rhythm with the conveyor. Each cut produces a center with squared ends and exposed layers. The centers may pass through a conditioning zone before chocolate coating. Their surface temperature must match the enrobing conditions. Warm centers can make chocolate slide. Cold centers can make chocolate set before it spreads. The chocolate used for coating is prepared in another system. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are mixed into a thick chocolate mass. The mixture passes through refining rollers that reduce particle size. This creates a smooth texture instead of a gritty one. The refined chocolate moves into conching equipment. Heavy arms work the mass under controlled heat. Fat spreads around the dry particles. The chocolate becomes smoother and more fluid. Before the chocolate reaches the enrober, it is tempered. It is cooled and gently warmed through a specific temperature sequence. This creates stable cocoa butter crystals. Tempered chocolate sets into a firm shell with a smooth surface after cooling. The conditioned Snickers centers then enter the enrober, where the chocolate curtain covers them completely. After the blowers and vibration section, the coated bars move into the cooling tunnel. Chilled air flows around the bars from above and below. The chocolate begins to crystallize. The surface changes from liquid shine to a firm shell. The soft nougat and caramel remain inside, protected by the coating. Cooling is controlled carefully. If it is too fast, the shell can crack or look dull. If it is too slow, the bars smear on belts and guides. The tunnel balances belt speed, temperature, and airflow until the coating is stable. At the exit, the bars pass through inspection. Cameras check coating coverage, broken corners, exposed caramel, exposed nougat, surface marks, incorrect length, and deformed shape. Metal detectors scan the product stream. Bars outside the programmed limits are rejected automatically. Accepted bars move toward wrapping. Timing belts space them evenly. Guide rails align each bar lengthwise so it enters the wrapper straight. Printed film unwinds from a roll. Tension rollers keep the film smooth. Registration sensors read printed marks and synchronize the wrapper graphics with each bar. The film folds around the bar through a forming box. A longitudinal seal closes along the underside or back. Heated sealing wheels press the film layers together while the bar continues moving. Cross-seal jaws close the front and back ends of each pack. They seal and cut at the same time, separating one wrapped Snickers from the continuous film tube. Wrapped bars pass through check weighers. A broken bar, missing bar, or incorrect product creates a weight outside the target range and is rejected. Vision systems inspect seal quality, wrapper alignment, code placement, and print registration. A coding unit applies production information to the wrapper or outer pack. The mark is small, sharp, and placed while the pack moves at full speed. Single bars may move directly to case packing. Multi-pack formats branch into another grouping stage. Several wrapped bars are gathered by belts and mechanical guides. The group enters a secondary film wrapper or paperboard carton. Hershey's chocolate production begins when a thick brown chocolate mass is squeezed between refining rollers until its coarse texture becomes smooth enough for a finished bar. The mixture entering the refiner is not ready to mold. It contains cocoa ingredients, sugar, milk components, cocoa butter, and other fats blended into a heavy paste. The particles are still too large. If the bar were made at this stage, the texture would feel gritty instead of smooth. The refiner uses closely spaced rollers to reduce the particle size. The chocolate paste is pulled through narrow gaps under pressure. Each pass breaks down sugar crystals, cocoa particles, and milk solids into a finer structure. The paste becomes thinner in texture, more uniform, and better suited for the next stage. Before the chocolate reaches this point, the cocoa stream begins with roasted cocoa beans. The beans are cleaned, sorted, and roasted to develop flavor and loosen the outer shells. After roasting, the beans pass through cracking equipment. The brittle shells break away from the inner cocoa nibs. Winnowing equipment separates the lighter shells from the heavier nibs using airflow and screening. The nibs continue into grinding. As they are crushed, cocoa butter inside the nibs melts from the heat of friction, turning the dry pieces into a flowing cocoa liquor. This dark liquid becomes one of the main foundations of the chocolate. Milk chocolate production also needs milk ingredients. Milk powder or other prepared milk components are measured into the mixing system. Sugar is dosed separately. Cocoa butter or additional fat is added to control flow and texture. The ingredients come together in mixers that fold the dry and liquid phases into a uniform paste. This paste is the material that enters the refining rollers. Once refined, it moves into conching equipment. Conching is a long mechanical working stage. Heavy arms, rollers, or blades push and fold the chocolate continuously under controlled temperature. Inside the conche, the chocolate becomes smoother and more fluid. Fat spreads around the tiny dry particles. The mass loses rough edges in texture and develops the flow needed for molding. The movement is slow, heavy, and constant, like thick liquid being polished from inside. The chocolate's viscosity is adjusted during this stage. It cannot be too thick, or it will not flow cleanly into molds. It cannot be too thin, or it will not hold the correct bar structure. The conche brings the chocolate toward the exact behavior needed for high-speed depositing. After conching, the chocolate passes through storage tanks. These tanks keep it warm and moving. Slow agitators prevent settling and maintain even temperature. From here, the chocolate is pumped toward tempering. Tempering is the stage that prepares the chocolate to set correctly. The warm chocolate is cooled, then gently reheated through a controlled temperature curve. This creates stable cocoa butter crystals inside the liquid chocolate. Without proper tempering, the finished bar could become soft, dull, streaked, or weak. Properly tempered chocolate sets with a firm structure, smooth surface, and clean break. The liquid remains pumpable, but its internal crystal structure is ready for molding. The tempered chocolate flows into the molding line. Rows of empty bar molds move beneath depositor nozzles. The molds are usually made from rigid plastic or metal and contain the exact shape of the finished Hershey's bar, including its rectangular outline and raised segmented pattern. The depositor releases a measured amount of chocolate into each mold cavity. The chocolate spreads across the base and into the corners. It fills the raised letter and segment details from below, because the mold holds the bar pattern in reverse. The molds pass through a vibrating table immediately after filling. The vibration settles the chocolate and removes trapped air bubbles. Small bubbles rise to the surface and break. The chocolate levels out, filling every corner and detail of the mold. The filled molds now enter a cooling tunnel. Chilled air flows around them while the chocolate begins to crystallize. The surface touching the mold firms first. The center of the bar sets more slowly. The stable crystals created during tempering guide the full bar into a solid structure. Cooling must be carefully controlled. If it is too fast, the bar can contract unevenly or form surface defects. If it is too slow, the chocolate remains soft and cannot release from the mold cleanly. The tunnel balances air temperature, humidity, and travel time. As the bar cools, it contracts slightly. This small shrinkage helps it separate from the mold surface. When the mold reaches the demolding area, the chocolate is firm enough to release without bending. The molds invert or flex lightly. Mechanical taps or vibration help the bars drop onto a conveyor. Each bar lands with its molded face upward or is turned into the correct orientation for wrapping. The surface now shows the familiar segmented shape. The empty molds return to the filling station. They may pass through inspection or cleaning before receiving the next chocolate deposit. The molding loop continues continuously, with empty molds becoming filled molds, cooled molds, demolded molds, and empty molds again. The demolded bars move through inspection. Cameras check shape, surface marks, missing corners, air holes, dull patches, broken segments, and incorrect release. Bars outside the program limits are removed automatically. Metal detection scans the product stream before wrapping. Accepted bars continue toward the wrapping line. Timing belts space them evenly. Guide rails align each bar lengthwise. The wrapper must meet every bar at the same position, so spacing and orientation are tightly controlled. For a standard chocolate bar, printed wrapper film or foil-backed material unwinds from large rolls. Tension rollers keep the material smooth. Registration sensors read printed marks so the wrapper design lines up correctly with the chocolate. The bar enters a flow wrapping system. The wrapper folds around it to form a tight package. A longitudinal seal closes along the back or underside. Heated sealing wheels press the material together while the bar continues forward. Cross-seal jaws close the two ends of the wrapper. They seal and cut the package from the continuous film. Each wrapped bar leaves as a separate unit with the chocolate protected inside. Some Hershey's bar formats use an inner wrap and an outer paper band. In that route, the chocolate first receives a protective foil or film layer. Then a printed paper wrapper folds around the outside. Folding plates, belts, and tucking fingers create crisp edges around the rectangular bar. Miniature bars follow the same basic idea on smaller equipment. Small molded pieces are aligned, wrapped in individual foil or film, sealed, coated, and sent toward bagging or carton packing. For bars containing inclusions, the chocolate process changes before molding. Almonds, crisped rice, cookie pieces, or other inclusions are prepared separately and fed into the tempered chocolate stream or deposited into the molds. The pieces must be dry and correctly sized so they do not clog nozzles or create weak spots. When inclusions are mixed into the chocolate, gentle agitation keeps them suspended. The depositor must deliver both chocolate and pieces evenly into every mold. The vibrating stage settles the mixture without allowing all inclusions to sink to one side. For filled or layered chocolate products, a shell molding process may be used. Chocolate is deposited into molds, then shaken or inverted to coat the cavity walls. After partial cooling, a filling is added, and more chocolate seals the base. The finished piece is cooled, demolded, inspected, and wrapped in a similar downstream sequence. For the classic solid bar, the process remains focused on molding a single continuous chocolate body. The segmented pattern helps the bar break into pieces later, but inside the factory, it also gives the product a precise shape that inspection systems can measure. Wrapped bars pass through check weighers. A missing bar, broken bar, or incorrect product weight causes rejection. Vision systems inspect wrapper position, seal quality, code presence, print alignment, and package damage. Ferrero Rocher is manufactured by assembling a layered sphere where a roasted hazelnut sits inside a wafer shell. The shell is filled with hazelnut chocolate cream. Then the whole piece is coated in chocolate and rolled in chopped hazelnuts before a final set and wrap. The process starts with hazelnut preparation because nut size and roast level define the center bite and also influence how the coating adheres. Raw hazelnuts are cleaned with screens and air separation, so stones and shells are removed. The nuts are graded by diameter, so the center nut fits the wafer cavity without forcing cracks. Roasting line heats the nuts to a target color and moisture. Roasting drives off water and develops aroma while keeping the nut interior crisp. After roasting, the nuts are cooled quickly, so residual heat does not soften the wafer later. Skins are removed after roasting because loose skin fragments create bitter specks and interfere with cream texture. Nuts pass through rubbers or abrasive rollers that loosen skins. Air aspiration lifts skins away from the heavier nut kernels. The cleaned nuts are then rescreened to remove broken pieces. Whole nuts are routed to center insertion. Broken nuts are routed to chopped nut streams or paste production. A portion of the roasted nuts is chopped for the outer layer. Chopping is done with calibrated cutters that create a narrow size band. The target size must be large enough to read as crunchy pieces. The target size must be small enough to adhere evenly to a wet chocolate surface. Chopped nuts are screened to remove fines because fines create dust and dull the finish. The chopped nut stream is held in dry, conditioned air so it remains free-flowing. Another portion of the roasted nuts is processed into hazelnut paste for the cream and chocolate phases. Nuts enter a grinding system where rollers or stone mills reduce them to a smooth paste. Grinding generates heat, so the paste line uses temperature control to avoid over-thinning. The paste is refined until particle size is below the gritty threshold. The paste is then held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a separate stream because wafer must be crisp and dimensionally stable. Wafer batter is prepared by blending flour with water and sugar and small amounts of fat. Mixing is controlled to hydrate flour while limiting gluten development. The batter is filtered to remove lumps that would block depositor nozzles. Batter viscosity is adjusted so it spreads evenly on heated plates. Wafer baking uses wafer irons that form thin sheets by heating both sides. The batter is deposited onto the plates and spread into a uniform film. Heat drives water out quickly and sets the wafer into a rigid, porous sheet. Baking time is tuned so the sheet dries to low moisture without scorching. The sheet exits and is cooled so it becomes crisp and easy to cut. To create the Rocher shell, the wafer is shaped into cups or hemispheres. One method presses warm wafer sheets into molded cavities and then trims the edges. Another method bakes wafer directly into formed shapes using shaped plates. Forming must avoid cracks because cracks allow cream leakage. The formed halves are inspected by size and by edge integrity. Wafer halves are then paired into hollow spheres. A joining step applies a thin line of adhesive cream or chocolate along the rim. Two halves are aligned and pressed together. Pressure is controlled so the seam closes without crushing the wafer walls. The joined shells are cooled briefly so the seam sets and the sphere stays rigid during filling. The filling cream is produced as a fat-based emulsion with suspended solids. Sugar and milk solids are blended with hazelnut paste and cocoa components depending on the target profile. The mass is refined so it becomes smooth and spreadable. Refining can be done with roll refiners or ball mills that reduce particle size. The cream is then conched or mixed under heat to remove moisture and to distribute fat. Final viscosity is tuned so it can be dosed into wafers without air gaps. Chocolate used for coating is prepared and tempered for stable crystallization. Chocolate is melted and filtered to remove unmelted particles. Tempering cools the chocolate and builds stable seed crystals. The chocolate is then brought to a working temperature that maintains flow. Viscosity is adjusted by temperature control and by cocoa butter balance. Stable viscosity is needed because coating thickness must be consistent. Filling the wafer sphere begins by dosing a layer of cream into the cavity. The dosing head inserts into the shell opening and dispenses a controlled volume. The shell rotates or indexes, so cream spreads along the inner wall. This creates a base that will hold the center nut. The volume is controlled to avoid excess that would squeeze out at closure. A whole roasted hazelnut is then placed into the center. Placement uses a singulation system that feeds nuts one by one. Each nut is aligned and dropped into the cream bed. The cream supports the nut and locks it in position. Nut placement must be centered so the final sphere balances during coating. Off-center, nuts create wobble and uneven chocolate thickness. After nut placement, the cavity is topped off with more cream. The second dose surrounds the nut and fills remaining void volume. The dosing profile is tuned to avoid trapping air around the nut. Air pockets can collapse during cooling and cause surface dents. The cream surface is leveled, so the opening can be sealed cleanly. Sealing closes the filled sphere, so the cream is enclosed. A wafer cap or a chocolate plug can be applied depending on design. If a wafer cap is used, it is bonded with a thin film of cream and pressed into place. If a chocolate plug is used, tempered chocolate is deposited to create a seal. The seal must be strong enough to survive later tumbling and coating. After sealing, the filled spheres are cooled to firm the cream. Cooling brings the fat phase into a stable crystal state. It also reduces cream tack, so spheres do not stick during transfer. Cooling is staged, so wafer does not absorb condensation. Humidity control matters because wafer crispness must be preserved. Once the centers are stable, the line moves into chocolate enrobing. The spheres pass through a chocolate curtain or a dipping system. Chocolate coats the surface and also acts as the adhesive for chopped nuts. Excess chocolate drains off as the spheres roll on a wire belt. A controlled vibration can smooth the coating and release trapped bubbles. Air knives can trim excess and define a consistent thickness. Immediately after chocolate coating, the spheres enter a nut coating stage. Chopped hazelnuts are applied while the chocolate is still wet. The spheres roll through a bed of chopped nuts, or nuts are showered from above. Rolling ensures full coverage across the sphere. Nut feed rate is tuned, so coverage is dense but not clumped. Excess nuts fall away and are recirculated after screening. Nut adhesion depends on chocolate temperature and set speed. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slow, nuts can slide and form bare patches. The process balances chocolate temper and cooling tunnel entry, so the surface remains tacky long enough for nut embedding. After nut application, the pieces enter a cooling tunnel that solidifies the chocolate. The cooling profile is staged to promote stable crystals. Early cooling sets the surface quickly, so nuts lock in place. Later cooling pulls heat out, gradually, to avoid contraction cracks. Final exit temperature is set, so pieces are hard enough for wrapping. During cooling, the internal cream also equilibrates. The cream-fat network continues crystallizing and becomes firmer. This improves bite and reduces oil migration. Temperature stability prevents bloom risk, and keeps the outer finish glossy. The wafer remains protected because the chocolate and cream act as moisture barriers. Some lines apply a final polish to reduce loose nut dust. A gentle tumbling or airbrushing step can remove unattached fragments. This step improves pack cleanliness and reduces debris in wrappers. It also reduces scuffing during downstream handling. Sorting and inspection occur before packaging. Vision systems can detect incomplete nut coverage and shape defects. Weight checks confirm fill and nut presence. Rejects are diverted so only uniform pieces reach wrapping. Metal detection can be used as a final integrity control. Cadbury chocolate begins as a controlled blend of cocoa components, dairy components, sugar, and fat that is refined into a smooth suspension, conched to stabilize flow and flavor, tempered to lock in stable crystals, then molded and packed, while temperature and viscosity stay inside a narrow window. Production starts with cocoa raw materials that arrive as beans or as processed cocoa ingredients, depending on the plant layout. When beans are used, they are cleaned first with screens and air separation, so stones and husk fragments are removed. The beans are then roasted in a programmed heat curve that drives off moisture and develops cocoa aroma while keeping scorch risk low. Roasting also makes the shells brittle, so separation is efficient later. After roasting, the beans are cracked and winnowed. Cracking breaks beans into nibs without pulverizing shells into fines. Winnowing uses airflow to lift lighter shell away from heavier nib. The nib stream is screened to remove oversized fragments that would strain grinders and to remove dust that would darken and overheat during milling. Nibs then enter grinding to become cocoa liquor. Grinding is a staged reduction where particle size drops while fat from the nib makes the mass flow. Early mills break nib into paste. Later mills refine the paste into a smoother liquor. Temperature is controlled because friction can raise heat and drive off aromatics. The goal is a stable liquor that is pumpable and consistent in solids and fat. Cocoa butter and cocoa powder streams are also managed. Cocoa butter is melted in jacketed tanks and filtered so no solid flakes remain. Cocoa powder is sieved to remove lumps that would create specks. These cocoa streams become levers for viscosity and flavor. More cocoa butter increases flow and melt. More cocoa solids increase intensity and thickness. Milk ingredients are prepared with the same attention to moisture and particle behavior. Milk powder is stored dry and sieved to break clods. Whey powders or lactose powders are handled similarly when used. These powders carry dairy flavor and also influence sweetness and caramel notes during later heating. Moisture in dairy powders must be low because water in chocolate drives thickening and seizing. Sugar is prepared as a clean, dry crystal feed. It is screened to control crystal size and remove agglomerates. Crystal size influences refining load and final mouthfeel. Fine sugar can reduce refining time but can increase dust and handling issues. Coarser sugar can slow refining and increase wear. The line selects a sugar specification that supports consistent refining performance. The first assembly stage is mixing, which creates a uniform pre-blend before refining. Cocoa liquor and melted cocoa butter enter a mixer and create a fat, continuous base. Sugar and milk powders are added gradually so they are wetted rather than floating as dry islands. Mixing uses a strong folding action to distribute powders through fat. The goal is a crumbly paste or thick dough depending on the recipe and the amount of fat present at this stage. In some milk chocolate processes, a crumb step is used to build characteristic dairy notes and to stabilize the milk solids. Crumb production combines milk and sugar with cocoa liquor or cocoa components and then heats the mixture to drive off water and develop flavor. The mixture is cooked until it becomes a dry, or semi-dry crumb material. The crumb is then milled and later remelted into chocolate mass. This approach changes flavor and texture because it sets milk sugars in a different thermal history. Whether crumb is used or not, the downstream steps still require refining and conching. Refining is the step that turns the mixed paste into a smooth eating texture. Refining reduces the size of sugar and cocoa and milk particles so the tongue cannot detect grit. This is often done with 5-roll refiners or with alternative milling systems. In DUR, roll refining the paste passes between rollers with decreasing gaps. Each pass squeezes and shears particles smaller. The output becomes thin flakes because the mass leaves the final roll as a film that breaks off. Refined flakes have low free fat at their surface and are prone to holding moisture and air. They must be processed immediately into conching. Conching is a combination of mixing, shear, and controlled heat that changes both flavor release and rheology. In conching, the flakes are worked in a conche where paddles or rotors knead the mass. Heat keeps fat fluid and encourages volatile removal. Shear coats particles fully with fat, which reduces friction and lowers viscosity at a given fat level. Conching is often described as 2 overlapping goals. One goal is flavor smoothing by driving off unwanted volatiles and distributing aroma compounds. The second goal is flow control by reducing moisture and breaking down agglomerates so the chocolate becomes a stable suspension. Moisture control is critical because even small water content can cause thickening. Conches, therefore, manage airflow and temperature so water leaves gradually without overheating. During conching, emulsifiers can be added to fine-tune flow. Lecithin is a common flow modifier and it reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further at the same fat level. These additions are dosed late because early addition can mask conching effects and can change shear behavior. Dosing is precise because small changes alter how chocolate runs through pumps and through molding heads. After conching, the chocolate is held in storage tanks with gentle agitation. Tanks keep temperature stable, so the chocolate remains fluid. Agitation prevents separation and keeps the suspension uniform. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is smooth and flavored, but it is not yet in the right crystal state for molding. Tempering is the controlled crystallization of cocoa butter that creates a stable set and a clean snap. Chocolate contains cocoa butter that can crystallize in several forms. Only specific forms give the desired gloss and contraction. Tempering builds a population of stable seed crystals and then holds the chocolate at a working temperature where these seeds guide solidification. Tempering is done in continuous tempering machines that heat and cool the chocolate in stages. The chocolate is first heated to melt existing crystals fully. It is then cooled while being agitated so crystals begin to form. It is then gently reheated to melt unstable forms while keeping stable seeds. The output is a chocolate that flows well, but contains the right crystal seeds. Process control uses temperature sensors and viscosity signals to maintain stability. Once tempered, the chocolate is ready for shaping. For bars, the main shaping method is molding. Polycarbonate molds move under deposit heads that meet a chocolate into each cavity. The depositor fills to a precise mass because bar weight must be consistent. Molds then pass onto a vibrating table. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate flow into sharp corners and improves surface gloss. After vibration, molds enter a cooling tunnel. Cooling is staged so the surface sets without shock. As chocolate cools, it contracts slightly. This contraction helps release from the mold. Cooling zones remove heat gradually so internal stress remains low. If cooling is too fast, the bar can warp or show bloom later. If cooling is too slow, throughput drops and molds remain occupied. When bars have solidified, they are demolded. Molds are flexed or tapped so bars release cleanly. The bars then move to inspection conveyors. Vision systems can detect surface defects and missing corners. Weight checks can confirm deposit accuracy. Defective bars are diverted for rework. Rework. Chocolate is collected and remelted, then reintroduced upstream in controlled ratios, so crystal history does not destabilize tempering. If the product includes inclusions like nuts or crisp pieces, the process adds an inclusion stage. Inclusions are prepared by roasting or drying and then screening to a tight size band. They are added either into the chocolate before molding or sprinkled into molds before depositing. Inclusion dosing must be consistent because it affects bar thickness and cooling time. Inclusion surfaces must be dry because moisture causes thickening and can create voids. If the product includes layered fillings, the line uses sequential depositing. A chocolate shell may be deposited first and partially set. A filling is deposited next. Another chocolate layer seals the top. This creates a composite bar that requires additional cooling time and more careful temper control. Even then, the same fundamentals apply. Each phase must flow at the right viscosity and set in the right order. Once bars are fully set, they move to wrapping. Wrapping is a mechanical process that protects chocolate from oxygen and moisture and from handling marks. Bars are fed into a flow wrapper or into a fold wrap system depending on the pack style. The wrapper forms film around the bar and makes seals. Seal temperature and dwell are controlled so the film closes without wrinkles. Film tension is controlled so it does not crush the bar edges. Toffee is manufactured by assembling a layered piece in a fixed cavity sequence, where a caramel cup is formed first, a hazelnut is seeded into that cup, a hazelnut cocoa cream is deposited around the nut, and a final chocolate cap is applied before cooling and tray packing. Production starts with preparing the two high-volume mass streams that define the piece. One stream is a caramel that must be firm enough to hold a cup shape, yet soft enough to bite cleanly. The other stream is a nut cream that must be smooth and pumpable, yet stable enough to keep its shape around the nut. A third stream is tempered chocolate for the cap and for any sealing functions. Caramel manufacturing begins with sugar and glucose syrup handling. Sugar is screened so crystal size is consistent and clumps are removed. Glucose syrup is held in jacketed tanks so viscosity stays stable for accurate pumping. Dairy components are prepared as a controlled liquid or powder stream depending on the recipe design. Fat is melted and filtered so it can be kneaded smoothly into the cook. Cooking is done in a continuous cooker or a batch kettle that is designed for high solids confectionery. The syrup phase is heated to dissolve sugar and drive off water. Solids level is the key target because it controls final chew and flow at the depositor. If solids are too low, the caramel will slump in the mold and stick in tooling. If solids are too high, the caramel becomes glassy and cracks when formed into thin walls. Temperature and residence time are tuned so browning develops to the desired level without scorching. As the cook reaches endpoint, the caramel is cooled to a working temperature where it remains plastic. Cooling is staged so viscosity is stable across the run. The caramel is held in a jacketed tank with gentle agitation to prevent skin formation. This tank feeds the forming depositor through heated pipes that avoid cold plugs. Flow meters and pressure sensors keep the depositor feed steady. Hazelnut handling runs in parallel. Nuts are cleaned and graded so the size band matches the cavity. Roasting drives moisture down and develops aroma while keeping the nut crisp. Cooling follows immediately, so residual heat does not soften caramel or melt cream fats later. Skin removal reduces bitter flecks and improves adhesion in the cream stage. Whole nuts are then singulated so they can be placed one by one. The hazelnut cocoa cream is prepared as a fat, continuous paste. Roasted hazelnuts are milled into a smooth nut paste with controlled temperature so oil does not separate. Sugar and cocoa solids and dairy solids are blended into this paste. Refining reduces particle size so the cream feels smooth rather than gritty. The cream is then mixed under controlled heat so viscosity becomes consistent and air is minimized. Emulsifiers can be introduced to tune flow and prevent oil bleed. The finished cream is held warm enough to pump but cool enough to keep flavor stable. Chocolate for the cap is produced and tempered to a stable crystal form. Chocolate is melted and filtered so no unmelted fragments remain. It is then tempered in a continuous tempering unit that heats and cools in stages. The goal is a chocolate that flows well but sets fast with gloss and clean release. Viscosity is monitored because cap thickness depends on flow through small nozzles. Assembly begins on a tray or belt line that carries a field of cavities. The cavities act as the master geometry for the product. Each cavity receives each component in sequence with tight timing. The first operation deposits caramel into each cavity as a measured shot. The shot is designed to form a cup rather than a flat puddle. This is done by using nozzle geometry and deposit motion that pushes caramel up the cavity walls. Immediately after deposit, a forming tool can shape the caramel cup. A punch or dome tool presses into the caramel to create a bowl profile. Tool temperature is controlled so caramel does not smear or stick. Dwell time is short, so the line speed remains high. The tool retracts and leaves a consistent hollow with a defined rim thickness. Caramel cup geometry is a major control point. Wall thickness must be thick enough to hold during nut insertion. Wall thickness must not be so thick that the bite becomes overly chewy. Rim geometry must be clean because the rim later interfaces with cream and the chocolate cap. If the rim is uneven, the cap can sit crooked and leave gaps. After cup forming, the cavities pass through a short cooling section. This cools the caramel surface to increase strength for nut insertion. Cooling is tuned to firm only the surface layer while keeping the bulk plastic. A fully hardened caramel would crack when a nut is pressed in. A too soft caramel would allow the nut to sink and deform the cup. Nut insertion follows. Nuts are fed from a singulator that orients each nut. A placement head drops or presses one nut into each caramel cup. Placement force is controlled so the nut seats at a consistent depth. The nut must be centered so the final piece balances. Off-center nuts can create thin caramel walls that tear. The nut is pressed enough to anchor without breaking the nut. Next, the nut cream is deposited around the nut. The depositor nozzle enters the cavity and dispenses a controlled volume. The cream must flow around the nut and fill the annular space. It must also avoid trapping air under the nut or along the cup wall. To control air, the deposit can be staged as a first ring and then a top fill. The nozzle motion can trace a small circle to wet the wall evenly. Cream viscosity is tuned for this step. If the cream is too thin, it floods and can overflow the rim. If it is too thick, it bridges and leaves voids. Void formation is a defect because it weakens structure and creates visual gaps under the cap. The line controls cream temperature tightly because temperature is the fastest way to shift viscosity without changing formulation. After cream deposit, the surface is leveled. A small leveling blade or vibration can flatten the cream surface. Leveling ensures the chocolate cap will sit evenly. It also ensures the cap seals the cavity edge without a high spot that would break later. Leveling is gentle because excessive vibration can move the nut and distort the cream ring. Chocolate capping follows immediately after leveling. Tempered chocolate is deposited as a disc onto the cavity opening. The disc must bond to the cream and rim and then set without cracking. Deposit weight defines cap thickness, which controls snap and protects. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber, where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station, where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion, with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, the mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill-seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems. Nutella biscuits manufacturing begins with production of the biscuit shell using a rotary molding and baking process. The biscuit dough is prepared by blending wheat flour with vegetable fats and powdered sugar inside a continuous horizontal mixer. The mixer operates at fixed low speed to prevent gluten development while ensuring even dispersion of fat particles across the flour. Water is added near the end of the cycle to activate binding. The dough is mixed until it reaches a defined plasticity suitable for molding and is then discharged into a feeding hopper connected to the forming line. The rotary molder presses the dough into engraved cavities on a rotating drum. The cavities have an open bottom design to release formed biscuits onto a steel mesh conveyor belt. The upper roller applies pressure to ensure full cavity fill, while the scraper removes excess dough and reintroduces it into the system. Each molded shell includes a circular depression designed to receive the Nutella filling after baking. The unbaked shells are spaced at regular intervals on the conveyor to allow for controlled baking conditions. The biscuit shells are conveyed into a multi-zone tunnel oven for baking. The tunnel consists of top and bottom heating elements, independently controlled in each zone. The oven temperature rises gradually from 160 to 210 degrees Celsius across the length of the tunnel. The baking profile is optimized to achieve full moisture removal from the dough without causing expansion or deformation of the molded cavity. Residence time in the oven is calibrated to match dough moisture content and thickness. Shells exit the oven fully baked with crisp structure and low residual humidity. After baking, the biscuit shells are cooled using ambient air directed across multiple conveyors arranged in a serpentine path to reduce surface and internal temperatures evenly. Cooling is required to stabilize the biscuit structure and prepare the cavity for Nutella filling. The biscuits are held at rest until their surface temperature falls below 30 degrees Celsius to prevent filling separation. In parallel, the Nutella filling is prepared in a high-shear emulsification unit. Using sugar, skimmed milk powder, cocoa, hazelnut paste, and vegetable oils. The ingredients are pre-mixed in separate feeders and metered into a blending vessel. The vessel operates under vacuum to remove entrapped air and maintain smooth consistency. The filling is processed at controlled temperature of 40 to 45 degrees Celsius to keep the viscosity within a defined range suitable for extrusion. Once homogenized, the filling is pumped to a filling head fitted with multiple nozzles. The cooled biscuit shells are conveyed under the filling head where each cavity is aligned with a single nozzle. A volumetric piston system injects the Nutella filling into each cavity with precise volume control. The fill level is calibrated to rise just below the edge of the biscuit wall to allow sealing with the top biscuit layer. After filling, the open surface is inspected for overflow or inconsistency using machine vision systems that communicate with rejection gates for off-spec product. A second biscuit layer is prepared using a similar dough mixing and molding process, but with a flat profile and no cavity. These flat biscuits are baked and cooled on a parallel line. After cooling, they are conveyed to the sandwiching station where they are aligned and placed on top of the filled biscuit shells. Robotic arms or mechanical pushers perform the alignment and placement. Each top biscuit is pressed gently to create full contact with the Nutella surface, ensuring mechanical bonding through surface tension of the fat-based filling. The sandwich biscuits enter a brief setting tunnel where cool air is applied to solidify the outer edges of the filling. This step reduces movement during handling and packaging. The biscuits exit the tunnel with the Nutella core enclosed between two baked shells. Completed Nutella biscuits are conveyed to a wrapping line. Each biscuit is separated by timing belts and transferred to a horizontal flow wrapping machine. Printed film is pulled from a roll and formed into a tube by a forming collar. The biscuit enters the tube, and the machine applies a longitudinal heat seal using rotating pressure rollers. End seals are created using heated sealing jaws that cut and close the wrapper simultaneously. Wrapped units are transferred to a grouping station where multiple biscuits are oriented into lanes and grouped for final packaging. Mechanical pushers move the groups into pre-formed trays or cartons, which are closed and sealed using hot melt glue. Cartons are held under compression for a fixed time to ensure glue adhesion before being moved to the final packing area. Each element of the Nutella biscuit structure is formed in distinct production zones that operate in parallel and converge during assembly. The biscuit shell relies on controlled dough plasticity, consistent cavity shaping, and uniform baking to maintain its geometry. The filling requires stable emulsification and thermal regulation to maintain deposition quality and shelf stability. Assembly depends on mechanical alignment, volumetric precision, and sealing reliability. Material flow through the plant is linear with dedicated conveyance systems connecting each station. Biscuit shells and tops are kept on separate synchronized lines to ensure timing consistency during sandwiching. The filling pump rate and nozzle actuation are matched to biscuit speed to maintain throughput. Each station includes real-time sensors to monitor dough consistency, bake color, biscuit thickness, fill weight, and seal integrity. These sensors feed data to a central programmable logic controller that adjusts line speed, pump rate, and heating elements based on tolerances. The manufacturing of Nutella biscuits depends entirely on coordinated dosing, shaping, heating, cooling, filling, sealing, and wrapping processes. Every stage transforms the materials physically by temperature or mechanical force, without the use of molding or batch processing beyond the initial dough and filling prep. All thermal zones are closed-loop systems with adjustable airflow and temperature feedback. Air velocity, humidity, and direction are optimized to control baking profiles and cooling rates. These variables determine final texture and filling retention. Filling viscosity is adjusted by temperature control and shear rate. The shear thinning nature of the filling allows fast deposition while maintaining form when static. Deposit shape is retained until enclosed by the top biscuit and set during the cooling phase. Final product dimensions are defined by the cavity shape of the rotary mold and the flatness of the sealing biscuit. Mechanical indexing ensures positional accuracy for every fill and seal. No lateral shift is tolerated at the sealing station. The top biscuit must be seated with uniform pressure to prevent leakage or deformation. This step is controlled by pneumatic actuators that apply force within a calibrated range to prevent structural damage to the shell. The flat biscuit must align concentrically with the base. All scrap or off-spec products are diverted to return belts for reprocessing or rejection. These include unfilled shells, misaligned sandwiches, overfilled units, and wrapping errors. Each rejection path is physically separated to maintain uninterrupted flow of conforming units. Finished wrapped units pass a final weight check and metal detection station before secondary packaging. Cartons are printed, coded, sealed, and stacked for dispatch. No rework is conducted beyond primary quality rejection zones. Oreo production starts with the preparation of the chocolate biscuit dough using a high-capacity continuous mixer. Dry ingredients including soft wheat, flour, sugar, cocoa powder, and leavening agents are first weighed and fed into the mixing chamber. A separate line introduces palm oil or shortening, which is preheated to maintain fluidity and evenly distributed across the dry blend. Water is added gradually to initiate dough formation while mixing paddles rotate at low speed to prevent overdevelopment of gluten. The process continues until the dough reaches uniform consistency with defined plasticity suited for rotary molding. The mixed dough is conveyed to the forming system via an auger feed mechanism. The dough enters the hopper of a rotary molder, equipped with engraved rollers that define the embossed biscuit design. As the dough passes through the rollers, it is pressed into the cavities with precise pressure and then released onto a wire mesh baking band by means of a stripping knife. Excess dough is scraped from the roller surface and returned to the feed hopper for reuse. Biscuits are formed in continuous rows and spaced evenly to allow thermal exposure during baking. The molded biscuit pieces are carried into a multi-zone tunnel oven. The baking process is divided into sequential zones where temperature and air velocity are independently controlled. The oven begins at a moderate heat to set biscuit shape and rises to higher temperatures to complete internal baking and develop surface color. The typical baking curve ranges from 160 to 220 degrees Celsius. Each biscuit remains in the oven for 6 to 9 minutes, depending on thickness and moisture content. The mesh band allows uniform exposure to heated air on all sides. After baking, the biscuits are discharged onto a cooling conveyor where ambient air is directed from above and below to bring the temperature down gradually. The biscuits move across multiple levels or loops of conveyors to extend cooling time without occupying additional floor space. Final biscuit temperature is reduced to below 30 degrees Celsius to ensure structural stability before sandwiching. Simultaneously, the creme filling is prepared in a separate emulsification line. The filling consists of icing sugar, hydrogenated vegetable oil, soy lecithin, and flavoring agents. Ingredients are loaded into a planetary mixer equipped with high-speed blades and jacketed walls. The sugar is ground and combined with oil under shear to produce a smooth, homogeneous, fat-based paste. Temperature is maintained between 35 and 40 degrees Celsius to control viscosity and ensure pumpability. Once mixed, the filling is transferred to a holding tank fitted with agitators to prevent settling or phase separation. The cooled biscuits are conveyed into the sandwiching station in a synchronized line. They are separated into top and bottom rows using mechanical diverters. The bottom biscuits move directly under the filling depositor, while the top biscuits follow a delayed path to allow time for the filling application. The depositor contains multiple nozzles aligned with each lane of biscuits. Each nozzle dispenses a fixed volume of cream using a positive displacement piston pump. The deposit is placed at the center of each biscuit with consistent diameter and height. Top biscuits are aligned and placed onto the filled base biscuits by a pick and place mechanism. A servo-controlled arm picks the top halves and lowers them precisely onto the creme layer. The contact pressure is adjusted to spread the filling evenly without causing overflow. The result is a sandwich structure with a defined creme layer held between two embossed chocolate biscuits. Each finished sandwich is inspected for alignment and fill consistency using vision sensors and rejected automatically if outside tolerance. Sandwiched Oreos are then conveyed to the packaging section. The product flow is timed to match the entry speed of the horizontal flow wrapping machine. Wrapping film is unrolled and passed through a former to create a continuous tube. The Oreos enter the tube and are enclosed longitudinally using heated crimp rollers. Transverse end seals are applied using rotating sealing jaws that cut and seal each package simultaneously. Seal parameters are adjusted for film thickness and product temperature. The wrapped Oreos exit the machine in a sealed pillow pack configuration. Multiple wrapped packs are grouped into secondary packaging units using collection conveyors and counting gates. Depending on the product format, they may be stacked or aligned edge to edge and loaded into pre-formed cartons. Cartons are formed from flat blanks using folding arms and sealed with hot melt glue. Filled cartons are compressed briefly to ensure adhesive bond and discharged onto the final conveyor. Each line operates continuously and is monitored by sensors that track biscuit position, deposit weight, package seal integrity, and material usage. The entire process is controlled by a centralized PLC system that coordinates line speed, temperature settings, pump pressures, and mechanical alignment across all stages. Biscuit texture is determined by dough moisture content, oven temperature profile, and baking time. Creme consistency is controlled through oil phase properties, shear rate, and deposition temperature. Assembly quality is a function of alignment precision, deposit accuracy, and pressure applied during sandwiching. Packaging integrity depends on film properties, sealing jaw temperature, and dwell time. Throughout Oreo production, no stage is batch-based beyond initial mixing. Dough and creme preparation feed into continuous mechanical systems that deposit, shape, bake, cool, fill, and wrap in a single linear sequence. Ingredient transformation is physical through heating, mixing, and compression. Structural integrity is achieved by thermal setting in the oven and mechanical bonding during sandwiching. The shape and weight of each Oreo are determined by the engraved mold cavities and the metered deposit volume. The embossed pattern is preserved by controlled dough texture and low expansion during baking. Biscuit brittleness is managed by adjusting water content and baking duration. Fill height is maintained by calibrating piston stroke length and pump cycle frequency. Every motion in the line contributes to dimensional uniformity and output consistency. Dough movement is regulated by roller speed and auger feed rate. Biscuit placement is defined by indexing and lane spacing. Creme application depends on nozzle diameter and internal deposit pressure. Sandwich closure requires precise Z-axis movement and timed application force. The rotary molding drum is cleaned automatically using scraper blades and air jets between production runs. Dough formulation is adjusted in real time based on humidity and flour batch variation. Viscosity of the creme filling is monitored using inline viscometers that signal temperature adjustments in the holding tank jacket. Oven parameters are logged continuously and used to regulate the baking curve. The production of Oreo cookies involves multiple heat and shear-based unit operations that alter physical properties without any fermentation or leavening beyond minor chemical agents. All dimensions are mechanically imposed and retained by careful control of thermal transitions and compression events. No rework is introduced into the sandwiching process. Only biscuits that meet shape, color, and thickness criteria are accepted. Filling rejects are filtered back into the holding tank through a return line. Packaging errors are removed before sealing to prevent final product contamination. The system is designed to maintain flow and reject outliers without stopping. The final Oreo structure consists of 2 rigid outer shells and 1 malleable creme layer. The shells resist deformation under handling. The creme adheres without fluid migration. Moisture barrier properties are maintained by the biscuit's low water activity and the hydrophobic nature of the fat-based filling. Nutter butter cookie production begins with the preparation of the peanut-flavored dough. Dry base materials are loaded into a large capacity horizontal mixer through automated dosing systems. These materials include soft wheat flour, granulated sugar, dextrose, baking soda, salt, and peanut flour. Separately, hydrogenated vegetable oil and peanut butter are preheated in jacketed holding tanks to reach a flowable state. The fats are pumped into the mixer and distributed over the dry mix, while the paddles rotate at low speed. Water is then injected into the chamber through spray nozzles to activate hydration without overdeveloping gluten. Dough temperature is maintained between 18 and 22 degrees Celsius. The dough is mixed until a target plasticity is achieved, ensuring it can be molded without sticking or tearing. Once complete, the dough exits the mixer via a discharge chute and is conveyed to a dough feed hopper mounted above a rotary molder. The molder is equipped with engraved rollers featuring the signature peanut shell pattern and split mold design that will define the top and bottom cookie pieces of the Nutter Butter sandwich. As the dough is fed into the rotary molder, the engraved drum compresses and shapes the dough into uniform cookie halves. A fixed scraper blade removes excess dough from the roller's surface, while a vacuum-assisted mechanism ensures accurate demolding from the cavities. Formed cookies are transferred onto a wire mesh conveyor belt that transports them through a continuous tunnel oven. Excess dough is rerouted via a return auger and refed into the forming system. The tunnel oven is divided into sequential thermal zones with independent temperature control. The initial zone sets the cookie shape at approximately 160 degrees Celsius. The intermediate zones raise temperature to 200 degrees Celsius to drive off internal moisture. The final zone applies finishing heat at 220 degrees Celsius to develop the surface texture and light browning. Airflow direction and volume are adjusted separately for top and bottom heating across all zones. The wire mesh belt permits full convection exposure around each cookie piece. Total baking time ranges from 6 to 9 minutes depending on dough moisture, product thickness, and belt speed. During baking, moisture content is reduced from around 18% to below 2%. The cookies exit the oven fully formed and structurally rigid. They are conveyed to an ambient cooling system composed of multi-tiered belts with forced air circulation. Cookies must reach below 30 degrees Celsius before proceeding to filling. While the cookies cool, the peanut butter creme filling is produced in a separate, continuous emulsification system. The formulation includes icing sugar, hydrogenated vegetable oil, roasted peanut paste, salt, and emulsifiers such as mono and diglycerides. The ingredients are metered into a vacuum mixer fitted with high-speed rotating blades. The mixer maintains low pressure to prevent air incorporation, while the fat and sugar blend into a smooth paste. Product temperature is held between 38 degrees Celsius and 42 degrees Celsius to control viscosity and ensure deposit stability. The filling mass is pumped from the mixer into a stainless steel holding tank equipped with a slow agitator to maintain consistency. From there, the creme is fed through a positive displacement pump into a volumetric depositor that sits above the sandwiching conveyor. Cooled cookie halves are divided into bottom and top rows using a mechanical separator with indexed belts. The bottom halves are aligned and conveyed beneath the depositor. Each nozzle in the depositor corresponds to one cookie lane. As each cookie passes below, a metered quantity of peanut creme is dispensed onto the center of the bottom cookie surface. The deposit rate is synchronized with belt speed to maintain consistent fill weight and location. Top cookie pieces are then aligned with their corresponding filled bottom halves using a mechanical alignment rail. A pusher bar or servo-driven actuator lowers each top cookie onto the filling. The applied pressure is controlled to spread the filling to the desired diameter without squeezing it beyond the edge. The resulting sandwich maintains clean fill lines and full bonding across the contact surface. Assembled Nutter Butter sandwiches are conveyed through a short resting belt to allow any residual filling movement to stabilize. From there, they move into the packaging system. The first packaging stage consists of a flow wrapping machine fed by a timing belt that spaces cookies at fixed intervals. Wrapping film is unwound from large rolls and formed into a tube around the cookies using a forming collar. The longitudinal seam of the wrapper is sealed by heated crimp rollers, while the ends are cut and sealed by rotary jaws. Temperature and dwell time of the sealing jaws are set based on film thickness and line speed. The wrapped cookies exit the flow wrapper as individual units or twin packs depending on the product variant. Wrapped units are conveyed to a grouping system where multiple cookies are collected and inserted into multi-pack cartons. Mechanical pushers or robotic pick-and-place arms load the cookies into pre-glued cartons. Cartons are sealed using hot melt adhesive applied by contact nozzles. Glue setting is ensured by compression flaps and a short dwell section. The cartons are then labeled, coded, and discharged to case packing. Throughout the process, all movements are continuous and synchronized. Dough feed, forming, baking, cooling, creme preparation, depositing, sandwiching, and wrapping occur without manual intervention or batch holding. Each station is linked to upstream and downstream processes by belt conveyors, sensor arrays, and real-time control systems. The final texture of the Nutter Butter cookie shell depends on dough fat content, moisture level, forming pressure, and thermal profile. The filling spread and adhesion characteristics are governed by shear during mixing, fat phase structure, and filling temperature at deposition. The sandwiching step relies on timing and vertical alignment accuracy to avoid rotation or breakage. Rework is minimized through inline inspection at multiple points. Cookies with incomplete molding, overbake, off-center filling, or misalignment are removed by air rejection systems or diverted for grinding and remelting. Only fully conformed products proceed to final packaging. The design of the peanut shell shape is retained through rigid cavity molding, low dough expansion, and short baking time. Each cavity in the mold drum is precision machined to micron level tolerances. The emboss pattern depth controls final surface visibility. The moisture balance in the dough ensures sharp edge retention and minimal slumping during oven transit. The filling deposit pattern is a function of nozzle diameter, piston stroke length, deposit speed, and creme viscosity. The diameter of the final fill is determined by vertical pressure from the top cookie and the flow behavior of the fat matrix. The ratio between shell weight and filling weight is maintained within narrow limits to ensure structural integrity and mouthfeel. Line efficiency is governed by synchronization between forming rate, baking throughput, and filling capacity. Adjustments to belt speed, oven temperature, or depositor cycle timing propagate downstream. Any mismatch between stations can result in underbake, inconsistent fill, or packaging misfeeds. The mechanical layout of the Nutter Butter production line is linear and modular. Dough flows from mixer to molder. Biscuits flow from molder to oven. Creme flows from mixer to depositor. Sandwiches flow from depositor to wrapper. Each segment includes buffer zones to absorb variation and maintain steady output. Packaging formats can be switched by adjusting forming jaws, wrapping film feed width, and carton loader configuration. Line reconfiguration is managed through digital interfaces that adjust motion profiles, material flow paths, and spacing intervals. The final Nutter Butter product consists of 2 molded peanut-flavored cookies bonded with a central layer of smooth peanut butter creme. The top and bottom shells are symmetrical and embossed with the same pattern. The cream layer is centered and flush with the cookie edge. The finished unit exhibits uniform thickness, aligned sandwich halves, and sealed packaging with fixed weight. Each unit operation transforms the ingredients through shear, heat, pressure, cooling, or extrusion. No fermentation or chemical expansion occurs. All structural characteristics are mechanically imposed and thermally locked. The line operates at a continuous pace of thousands of cookies per hour. Consistency across units is maintained by regulating every input condition, from ingredient feed to forming pressure to deposit rate. All cookies follow the same linear path through the same physical conditions. The result is a uniform, mass-produced sandwich product with no variation in shape, weight, or filling distribution. The process begins with the preparation of the core ingredient, the peanut butter filling. Whole, dry roasted peanuts are delivered in bulk to the facility. These peanuts first enter a vibrating conveyor that removes loose skins and broken fragments. They pass under a high-powered magnet to eliminate any residual metallic particles. Then, the peanuts are gravity-fed into a stainless steel grinding chamber. Inside, large rotating blades crush the peanuts under high torque. The first grind reduces them to a coarse paste, maintaining some granular texture for mouthfeel. The paste is then pumped into a second stage grinder, equipped with finer burrs, reducing the particle size to below 20 microns. During this stage, a metered flow of salt, sugar, and hydrogenated vegetable oil is introduced via precision-controlled valves, ensuring consistent viscosity and sweetness across all batches. The resulting emulsion is routed through a jacketed pipe system, maintained at a specific temperature to keep the filling fluid enough for metering. This peanut butter flows into a holding tank fitted with an agitator that constantly stirs the mixture to prevent separation. The tank is linked to a high-speed depositor, which measures and dispenses precise volumes of the filling for the next stage. However, before the filling is used, the outer shell of the cup must be created. The outer chocolate coating begins with the mixing of ingredients: chocolate liquor, cocoa butter, milk solids, and sugar. These ingredients are loaded into a large-scale conche, a machine with heavy rollers that knead the mixture continuously for up to 12 hours. The conching process smooths out the texture and volatilizes undesirable flavors. After conching, the chocolate is pumped through a series of heated pipelines into a tempering unit. This unit cycles the chocolate through controlled heating and cooling zones to encourage the formation of stable cocoa butter crystals. This tempering process is crucial for creating a glossy finish and a crisp snap in the final product. Tempered chocolate is then delivered into the cup-forming system. Small polycarbonate molds, arranged in a continuous chain, move along a conveyor. At the first station, the molds are vibrated to eliminate air and then receive a precise amount of tempered chocolate. The molds pass beneath a rotary spinning unit that evenly distributes the chocolate along the interior walls, forming the shell. Rapid air jets cool and solidify the shell as it moves to the next station. Once the shell is set, the molds proceed to the filling line. Here, servo-controlled nozzles descend into each chocolate cavity and inject a precise volume of peanut butter filling. The temperature and flow rate are tightly regulated to ensure smooth deposition without overflow or disruption to the shell's integrity. As the filling sets, the molds continue moving to the capping station. At the capping station, a second layer of tempered chocolate is applied over the exposed filling to seal the cup. A gentle vibration removes trapped air and levels the surface. The molds then enter a refrigerated tunnel where they spend several minutes at sub-zero temperatures. This rapid cooling locks the structure in place and allows for demolding without cracking or warping. After cooling, the mold chain reaches the demolding station. A synchronized pusher mechanism nudges each mini cup out of its cavity. The cups drop onto a soft conveyor belt lined with food-grade cushioning material. From here, they are directed to an inspection line equipped with high-resolution cameras. These cameras scan each unit for surface defects, incorrect shape, or incomplete sealing. Any product that falls outside tolerance is automatically ejected via an air jet mechanism. Perfect cups continue along the belt to the wrapping system. The cups pass through a vibratory feeder that aligns them uniformly before entering the wrapping carousel. Here, pre-cut foil wrappers are fed from a roll and precisely positioned. A series of rotating arms wrap the foil around each mini, folding it into the familiar pleated skirt pattern. Heat-sensitive adhesives are applied in microdots to secure the foil in place without melting the chocolate underneath. The wrapped minis are then transferred to a bucket conveyor, which lifts them vertically to the weighing and portioning unit. This section uses a combination of multi-head weighers and vibration channels. Each head calculates the exact weight of its portion and releases it into a funnel only when the total matches the predefined package weight. The minis fall into open pouches below, which are already held in place by a form-fill-seal machine. As each pouch is filled, it moves to the sealing station. The top edges are pressed together between heated jaws that apply pressure and temperature simultaneously, creating an airtight seal. Excess air is evacuated prior to sealing to prevent bloating and ensure compact packaging. After sealing, each pouch is marked with a lot code and timestamp using a thermal inkjet printer for traceability. The sealed pouches drop onto a short accumulation conveyor that buffers the output before transferring them to a final packing station. Here, robotic arms pick up the pouches and place them into pre-formed cartons with precise orientation. The cartons are closed, sealed with hot melt adhesive, and stacked in layers onto shipping pallets using a gantry-style palletizer. Each completed pallet is automatically stretch-wrapped for stability and sent to storage for distribution. This entire process is governed by a centralized control system that monitors temperature, humidity, belt speed, deposition volumes, and flow rates. Real-time sensors feed data to a control panel, allowing technicians to make micro-adjustments and ensure batch-to-batch consistency. The system can run continuously for up to 24 hours without stoppage, capable of producing tens of thousands of minis per hour. Next, the focus turns to how raw materials are handled before entering production. Peanuts arrive in bulk tankers and are gravity discharged into underground silos lined with food-grade epoxy. Each silo is equipped with aeration systems to prevent moisture accumulation and ensure uniform temperature. The peanuts are pneumatically conveyed through stainless steel tubing into a vibratory feeder that meters the flow into a destining machine. This device uses oscillation and airflow to separate stones, soil particles, and foreign debris from the peanut stream. From there, the peanuts pass through a laser optical sorter that uses infrared and visible spectrum imaging to detect discolored or malformed nuts. High-speed air nozzles eject any flawed peanuts in milliseconds. Only uniform, high-grade peanuts proceed to the roasting unit. This unit is a continuous belt roaster with adjustable zones. Peanuts pass through multiple chambers where hot, dry air is circulated by impeller fans. Temperatures are carefully staged, rising from 120 to over 160 degrees Celsius, which drives out moisture and enhances flavor through Maillard reactions. Once roasted, the peanuts are cooled, using forced ambient air passed through a vibrating bed. This prevents residual heat from continuing the roast and ensures a consistent final color and texture. The roasted peanuts are then fed through a skin removal drum that uses abrasion and airflow to strip the outer skins. The clean peanuts are conveyed via vacuum lift to the grinding area, where the previously mentioned multi-stage grinding begins. Simultaneously, chocolate ingredients are stored in segregated silos and tanks. Sugar is kept in dehumidified environments to prevent caking. Milk solids and cocoa powder are transferred via screw augers into premix hoppers. Cocoa butter and chocolate liquor are maintained in heated jacketed tanks to remain fluid. All ingredients are automatically metered and conveyed to the conche for blending. The chocolate mass, after completing the conching phase, enters a holding tank fitted with constant agitation paddles to maintain homogeneity. From there, it's pumped into a multi-stage tempering system composed of a series of heat exchangers and temperature control zones. The chocolate is first heated to melt any remaining crystals, then rapidly cooled to initiate the formation of stable crystal forms, and finally brought back to a processing temperature that maintains its tempered state. This temperature is precisely held between 30 and 32 degrees Celsius, depending on the chocolate formulation. This tempered chocolate flows directly into a reservoir connected to the cup-forming depositor. This depositor features a rotating drum fitted with piston cylinders, each calibrated to dispense exact volumes of chocolate into the molds. As each polycarbonate mold tray moves beneath the depositor, the nozzles descend and fill each cavity with a metered dose. Immediately after deposition, the molds enter a vibrating station. Here, high-frequency vibrations cause the chocolate to flow evenly into the intricate cup recess, eliminating trapped air bubbles and ensuring the chocolate climbs uniformly up the sides. Next, the molds travel through a cooling tunnel set to gradually decrease the temperature. The tunnel is segmented into thermal zones that first solidify the outer edges of the chocolate shell and then slowly cool the entire form to prevent cracking. The movement through the tunnel is continuous and synchronized, with the chocolate shells emerging after a calculated duration with fully formed, hardened interiors. At this point, the molds reach the peanut butter filling station. A separate heated pipe system maintains the filling's viscosity, keeping it soft enough to flow but not hot enough to melt the chocolate shell. This balance is crucial. The filling enters a pressurized manifold, which feeds into a multi-head depositor equipped with servo motors. Each head aligns perfectly with the center of the chocolate shells and injects the filling with millisecond precision. The volume of filling is less than the total cavity depth, leaving room for the chocolate cap that will follow. As soon as the peanut butter is deposited, the mold trays pause momentarily while a burst of cool air is blown across their surface. This quick setting step helps firm up the top surface of the filling, preparing it for the capping stage without blending into the final chocolate layer. The capping process begins as the molds continue along a conveyor that passes beneath a second chocolate depositor. This unit mirrors the cup-forming depositor in design, but delivers a thinner stream of chocolate, just enough to create a smooth, flush surface over the peanut butter. The moment the cap is applied, the trays enter a second cooling tunnel with slightly lower humidity and temperature levels. This cooling tunnel runs longer than the first, allowing the entire assembly, base shell, filling, and cap, to solidify into a single bonded unit. Once fully cooled, the molded cups must be extracted without damaging their structure. At the demolding station, each polycarbonate tray is inverted over a soft silicone belt. Pneumatic actuators positioned above each cavity deliver a gentle burst of compressed air to eject the cups downward. The silicone belt cushions the fall and conveys the cups to a visual inspection zone. This inspection zone features an array of high-speed cameras positioned at multiple angles. Each cup is rotated in place as cameras scan for surface imperfections, discoloration, uneven capping, or malformed shapes. The system uses real-time image recognition algorithms to detect defects within milliseconds. If a unit fails inspection, it is marked by a food-safe dye jet and then removed further down the line by a robotic picker. Passing the inspection, the cups proceed into the foil wrapping module. The cups are gently aligned by centrifugal force in a rotating disc feeder. As each cup enters the wrapping station, it passes through a timing screw that spaces them evenly. Each cup is paired with a pre-cut foil sheet fed from a stacker. A vacuum arm lifts the foil and places it atop the cup just before it enters the wrapping drum. The wrapping drum rotates at high speed. As the cup and foil pass through its internal channels, shaped mandrels fold the foil around the cup. Fine-toothed wheels pleat the edges in the signature ruffled pattern. During this rotation, a microdot of adhesive is applied to the final fold, locking the wrap in place. The entire wrapping process takes less than 1 second per unit, with the machine capable of processing several hundred cups per minute. After wrapping, the minis exit onto a multi-lane conveyor. These lanes gradually converge into a single stream, where the minis fall into a vibratory channel that leads them to the multi-head weigher. This weigher consists of a circular array of hoppers, each continuously filled with minis. Load cells beneath each hopper constantly monitor the weight. The system's algorithm selects a combination of hoppers that together match the target pouch weight most precisely. Once the optimal combination is determined, the corresponding hoppers release their contents into a chute, which guides the minis into the waiting pouch below. The pouch is held open by mechanical grippers in a vertical form-fill-seal machine. This machine forms the pouch from a continuous roll of pre-printed laminate film. As the film unwinds, it passes through a forming collar that folds it into a tube. Vertical heat seal jaws bond the overlapping edges of the tube, while horizontal jaws seal the bottom to create the pouch base. The minis are then dropped into the open pouch, and the top is sealed immediately after filling. The sealing jaws apply precise heat and pressure, creating a strong, airtight bond. After sealing, each pouch travels under a printer head that marks it with production data, including time, date, and batch identification code. These markings are made using thermal inkjet or laser etching systems, depending on the packaging material. The printed pouch then passes through a final check weigher to confirm the net content. If underweight or overweight, the pouch is automatically diverted to a reject bin. The verified pouches proceed to the cartoning area. Here, a carton erector unfolds flat cardboard blanks and seals the bottom flaps with hot melt adhesive. Thus, open cartons are then conveyed to an indexing station, where robotic arms pick the filled pouches using vacuum grippers. These robots operate with vision guidance, ensuring the pouches are oriented correctly before placement. Each carton receives a set number of pouches, after which the top flaps are closed and sealed. Cartons then travel to the case packing area. Another robotic system groups the cartons into layers and places them into corrugated shipping cases. Each case is automatically labeled with barcodes and stacking instructions. Finally, the loaded cases are conveyed to the palletizing cell. Here, a 6-axis robotic arm equipped with suction cups lifts each case and arranges them on a wooden pallet in a tightly packed configuration. The completed pallet is wrapped with a stretch film using a rotating arm wrapper. This layer of plastic holds the cases together for transport, protecting them from moisture and movement. The entire pallet is then scanned for load integrity before being conveyed to the staging area, awaiting dispatch to distribution centers. All this activity is coordinated by a central manufacturing execution system. The MS tracks every movement and status of the materials, from peanut intake to finished carton. It interfaces with programmable logic controllers on the production floor to dynamically adjust machine settings based on real-time feedback. For example, if a slight shift in chocolate viscosity is detected, the MES can command the tempering unit to fine-tune the temperature curve. Similarly, if the peanut butter depositor records a higher than average flow rate, the filling head's piston stroke is automatically adjusted to compensate. Material traceability is ensured by RFID tagged ingredient containers and barcode scanned intermediate products. This allows every peanut butter cup mini to be traced back to the exact raw material batch it came from. Sensors track humidity and temperature at every stage, particularly within the cooling tunnels and storage silos. Even foil wrappers are logged and matched with machine lot codes. Automation is layered at every level. Pick-and-place robots replace manual handling. Vision systems eliminate the need for human inspection. Real-time analytics optimize yield and reduce waste. Redundant systems ensure that any malfunction is isolated without halting the entire line. Conveyor speeds are synchronized across zones to maintain timing continuity. The packaging line continues with precise, timed coordination as the sealed cartons are conveyed toward the aggregation system. This system groups multiple cartons into defined sets according to the final pallet configuration. A servo-controlled diverter arm separates cartons into staging lanes. Once the predefined group is complete, often in rows of 6, 8, or 12, an overhead gantry equipped with vacuum suction heads lowers onto the group, lifts the entire set, and places it into a corrugated master case. This movement is completed in a single fluid action to minimize cycle time. Before the master case is sealed, a leaflet or folded instruction insert, used for some international markets, is dropped into the case by a pneumatic feeder. The flaps of the case are then closed and sealed with twin hot melt glue nozzles, precisely depositing adhesive in a consistent bead along the contact edges. Immediately after the flaps are compressed shut, a set of pressure rollers moves over the top of the case to ensure uniform adhesion. Next, the sealed master case is conveyed under an inline labeling system. Here, a thermal transfer printer produces large format labels containing product SKUs, batch codes, barcodes, and destination identifiers. An applicator arm synchronizes with the moving case, slapping the printed label onto the side panel without stopping the line. A high-resolution camera follows, verifying that each label is present, legible, and properly aligned. If the label is missing or unreadable, the case is automatically diverted into a correction lane where a manual relabeling station awaits. From there, the master cases move toward the palletizing station. Palletizing begins with empty wooden pallets being fed from a stacker. An automatic destacker lowers and releases a pallet onto the loading zone. A vision-guided robotic arm reads the barcodes on incoming cases to determine their orientation and designated location on the pallet. Each case is picked up with a vacuum gripper or clamp-style end effector and rotated, if necessary, to match the programmed stacking pattern. Cases are placed in interlocked layers, alternating orientation by row to increase structural stability. As each layer is completed, a slip sheet is dispensed from a vertical magazine and dropped onto the layer before the next row begins. This adds friction between layers and protects the contents from compression. When the pallet reaches its full load height, typically 6 to 8 layers, the robotic arm disengages and the loaded pallet is conveyed to the wrapping station. At the wrapping station, the pallet is rotated on a turntable while a film carriage ascends and descends, dispensing stretch film under tension. The film is pre-stretched using powered rollers to increase load stability without using excess material. Once wrapping is complete, the film is cut and sealed using a heat blade, and a final top sheet of film is applied to provide dust and moisture protection. A cornerboard dispenser may apply vertical reinforcements along the pallet edges if required for export shipping. After wrapping, each pallet is routed through a check-in station equipped with RFID scanners and weight sensors. The data collected here is sent to the factory's logistics system, which assigns the pallet a dock number and dispatch order. Automated guided vehicles or laser-guided forklifts transport the pallet from the end of the line to the designated outbound dock. This end-of-line logistics system integrates seamlessly with upstream production data, allowing full visibility and traceability from raw ingredients to finished pallet. The factory's architecture is designed for just-in-time flow, meaning there is minimal buffer storage between stages. The speed and precision of every downstream step are tightly dependent on the upstream processes delivering product at the correct pace. Meanwhile, upstream processes like ingredient blending and chocolate tempering continue in a closed loop. The chocolate mass in the tempering unit is constantly monitored by inline viscometers and refractometers. These instruments send live data to the automated control system, which modulates the heating and cooling stages to keep the chocolate in its stable crystalline form. Any deviation in viscosity or temperature is corrected in real time by adjusting the flow of chilled or heated glycol in the jacketed lines. The peanut butter filling line operates on a similar control philosophy. The filling's consistency is maintained within strict tolerances using shear rate sensors and pressure transducers embedded in the deposit line. If a slight thickening is detected, a micro amount of vegetable oil is introduced upstream at the blending tank, rebalancing the emulsion. These corrections are automated and occur without interrupting production. To ensure continuous supply, the system uses dual tanks for both chocolate and peanut butter. While one tank feeds the depositor, the second is cleaned, refilled, or brought up to processing temperature. This tank switching sequence is managed by a series of automated valves and level sensors. When the active tank nears depletion, the system seamlessly switches to the secondary tank, ensuring an uninterrupted flow to the depositor heads. The mold handling system is another key area of automation. Molds are part of a closed-loop carousel that runs on synchronized drives and encoders. Each mold is equipped with an RFID chip embedded in its frame. This allows the system to track the position and status of every individual mold, whether it is empty, partially filled, cooling, or at the demolding stage. If any mold is flagged as defective, it is automatically diverted to a cleaning and inspection loop where high-pressure water jets and ultrasonic baths clean the mold before it re-enters production. The cleaning systems themselves operate on fixed intervals. Chocolate contact lines are flushed with a food-safe solvent followed by hot water, then dried with filtered air. The peanut butter system undergoes a similar process but also includes pigging, a technique where a cylindrical plug is pushed through the pipe to scrape residual filling. This ensures complete evacuation of material between batches and prevents buildup that could interfere with flow or hygiene. Another critical area is temperature management. Chocolate, peanut butter, and the air in various tunnels must be tightly controlled. The cooling tunnels operate with precision climate control using chilled glycol coils and air recirculation fans. The air inside each tunnel is filtered and dried to prevent condensation from forming on the cooling surfaces. Each tunnel is divided into zones, and the temperature in each is independently adjustable. This allows the product to be gradually cooled in stages, minimizing thermal shock and maintaining product integrity. The wrapping foil is also treated as a critical input. Foil rolls are stored in a humidity-controlled chamber and automatically loaded into the wrapping machines by robotic arms. Before entering the wrapping system, each roll is scanned with a spectrometer to verify that the foil's thickness, reflectivity, and coating align with specifications. Foil with even slight variations in thickness can cause machine misfeeds or affect the aesthetic of the final wrap. Every component, from the ingredient to the final unit, is integrated into a massive data collection system. Thousands of sensors measuring temperature, pressure, weight, viscosity, and speed generate real-time data that feeds into a plant-wide dashboard. This dashboard is monitored by a centralized control room that receives live alerts, trend reports, and predictive maintenance warnings. If a chocolate depositor starts running slightly slower than average, the system calculates whether this indicates wear on a motor, blockage in a pipe, or fluctuation in chocolate viscosity. A maintenance ticket is generated automatically, allowing for preemptive servicing before failure occurs. The same predictive logic applies to wear-prone parts like the foil wrapping mandrels, depositor pistons, or vacuum grippers. Cycle counts are tracked, and components are retired or serviced according to usage thresholds. This predictive maintenance ensures that the machines run at optimal efficiency with minimal unplanned downtime. Air quality within the production zone is also tightly regulated. The environment is filtered using HEPA-level air handling units that remove particulates and microorganisms. Positive pressure is maintained in clean zones to prevent contamination from adjacent areas. Even the flow of personnel and carts is controlled via airlock-style entry points and floor-level pressure mats that trigger sanitation protocols. The factory operates in a rhythm of continuous throughput. Each component, chocolate mass, peanut butter filling, molds, wrappers, pouches, cartons, pallets, flows through its respective subsystem at precisely regulated speed. The coordination of these movements relies not only on mechanical timing, but also on software orchestration. The entire plant is governed by a hierarchy of control. Field-level PLCs manage individual machines, line controllers handle sequences of machines, and supervisory control software integrates everything into a single process flow. Cadbury Dairy Milk is manufactured by transforming milk and sugar and cocoa into a low-moisture chocolate crumb or chocolate mass, refining it into a smooth suspension, conching it to stabilize flow, tempering it to lock stable cocoa butter crystals, then molding and packing while temperature and viscosity stay tightly controlled. Milk handling is treated as a structural step rather than a flavor step because dairy solids determine body and sweetness balance. Milk can enter as liquid milk, concentrated milk, or milk powder depending on plant design. Liquid streams are filtered and held at controlled temperature for predictable pumping. Powder streams are sieved to remove clods because clods do not hydrate evenly and later create texture specks. Sugar is screened to control crystal size and to remove lumps that would resist refining. Cocoa components are prepared as cocoa liquor and cocoa butter streams held warm so they remain pumpable. Cocoa powder streams are sifted when used to remove compaction lumps. All dry ingredients are kept low in moisture because water in chocolate causes thickening and unstable flow. A key feature of many milk chocolate lines in this style is crumb production, which converts milk and sugar into a dry solid that carries developed dairy notes and improves process stability. Crumb production starts by combining milk and sugar in a cooker. The mixture is heated while being mixed, so sugar dissolves and water begins to evaporate. Heating is controlled to drive off water without scorching milk solids. As water leaves, the mixture becomes thicker and begins to form granular solids. The cook continues until the mass becomes a dry or semi-dry crumb with low residual moisture. During crumb cooking, thermal history is tightly managed because it controls flavor development and functional behavior. Too gentle a cook leaves high moisture and produces crumb that later thickens the chocolate unpredictably. Too aggressive a cook darkens sugars and drives strong cooked notes that can overwhelm the profile. The endpoint is set by moisture content, and by the way, the crumb fractures when broken. When the endpoint is reached, the crumb is cooled and milled into a manageable size so it can be blended uniformly later. Cocoa liquor and cocoa butter are prepared in parallel. Cocoa liquor is held warm so it stays fluid and is filtered to remove solid lumps. Cocoa butter is melted in jacketed tanks and filtered for clean metering. These fat streams define the continuous phase of the final chocolate, and they also control viscosity through the downstream steps. Mixing combines crumb with cocoa liquor, cocoa butter, and additional sugar or milk solids as required by the recipe. The goal is to create a homogeneous pre-mass where solids are evenly distributed in fat. Mixing is done in high-torque mixers with wall scraping because the mass can be thick before refining. The mixture transitions into a paste with consistent color and no dry pockets. At this stage, the mass is not yet smooth. Sugar crystals and crumb particles are still large enough to be detected on the tongue. Refining is performed to reduce particle size. The pre-mass is fed to roll refiners or other milling systems. In roll refining, the mass passes through a series of rolls with decreasing gaps. Each pass squeezes and shears particles smaller. The refined output leaves the last roll as a thin film that breaks into flakes. These flakes have high surface area and must be processed into conching quickly to prevent moisture pickup. Conching is the step that transforms refined flakes into a smooth flowing chocolate with stable flavor. The flakes enter a conche where mechanical work coats each particle with fat and breaks down remaining agglomerates. Heat keeps cocoa butter fluid and supports moisture removal. Airflow through the conche carries away moisture and volatile compounds. Moisture removal is essential because even small amounts of water cause chocolate to seize and become thick. Conching also stabilizes rheology by reducing friction between particles. Early in conching, the mass can be dry and pasty. As fat distribution improves, the mass becomes smoother and viscosity drops. The concha profile is tuned to reach a target viscosity for molding and enrobing while maintaining the desired flavor. Over-conching can reduce throughput and strip some volatile character. Under-conching leaves high viscosity and inconsistent snap. Emulsifiers are typically added near the end of conching. Lecithin improves particle wetting and reduces yield stress. Another flow modifier can be used to reduce viscosity further at a given fat level. These additives are dosed precisely because small changes alter how chocolate behaves in deposit heads and tempering machines. The chocolate is then filtered and transferred to holding tanks with gentle agitation to keep the suspension uniform. Tempering is the controlled crystallization of cocoa butter that gives dairy milk its stable set and gloss. Chocolate is first heated to melt existing crystals fully. It is then cooled under agitation so new crystals form. It is then reheated slightly to melt unstable forms while keeping stable seed crystals. The output chocolate contains a controlled population of stable crystals and remains fluid at the working temperature. Temper is monitored continuously because it drives mold release and surface quality. If temper is too low, the chocolate sets slowly and releases poorly and can bloom later. If temper is too high, viscosity rises and the chocolate becomes thick, causing poor mold, fill and thick edges. Tempering machines adjust cooling and heating in small increments to maintain the target crystal content. Molding shapes the chocolate into bars and blocks. Polycarbonate molds are cleaned and pre-warmed to prevent condensation. Depositors meter chocolate into each cavity with tight mass control. The filled molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also improves detail in any embossed features. Cooling tunnels set the molded chocolate. Cooling is staged to set the surface quickly without creating internal stress. The chocolate contracts slightly as it cools, which helps demolding. If cooling is too fast, the chocolate can crack or warp. If too slow, the line speed drops and molds remain occupied. Cooling also must avoid condensation because moisture on the surface can cause sugar bloom. After cooling, the molds are inverted and the bars release. Release depends on correct temper and correct cooling because the bar must contract away from the mold wall. Bars transfer to conveyors where they are inspected for surface defects. Weight checks confirm deposit accuracy. Bars with defects are diverted for rework. Rework is remelted and returned upstream in controlled ratios so it does not destabilize tempering. If the product includes inclusions or filled formats, the molding stage expands. Inclusions, such as nuts, are screened and kept dry. They can be placed into molds before chocolate deposition or blended into chocolate with controlled suspension. Filled formats use sequential depositing. A shell is deposited and partially set. A filling is dosed and then sealed with a chocolate back layer. Cooling profiles are adjusted because fillings change heat transfer and can insulate. After demolding, bars move to wrapping. Wrapping protects chocolate from oxygen, moisture, and abrasion. Bars are indexed into wrapping machines that fold foil or film around each bar. Fold geometry is controlled so edges are crisp and seals are tight. If an inner foil and outer paper wrap are used, the foil provides the barrier and the paper provides stiffness and print. Heat sealing or crimping forms the closure, depending on wrap type. Coded information is applied during wrapping or immediately after. Vision systems check wrapper alignment and seal integrity. Check weighers verify pack weight. Wrapped bars are then collated into cartons if needed. Cartons are erected and filled with a defined count. Cartons are closed and glued. Finished units are case packed and palletized. The process control backbone for dairy milk is moisture management and particle size management and crystal state management. Crumb production drives moisture down and creates a stable dairy sugar matrix. Refining drives particle size down for smoothness. Conching drives off remaining moisture and stabilizes flow by coating particles with fat. Tempering builds the correct crystal population for gloss and snap and clean mold release. Cooling locks the structure and wrapping protects it from temperature swings and humidity. Three Musketeers is manufactured by producing a highly aerated chocolate-flavored nougat center, forming it into a continuous slab, cutting it into bars, enrobing those bars in tempered chocolate, then cooling and wrapping while density and coating thickness remain tightly controlled. The defining step is the aeration system, because the bar's texture depends on holding a large volume of fine bubbles inside a stable sugar and fat matrix. The process, therefore, starts by building two streams that can be combined without collapsing air cells. One stream is a cooked syrup with a precise solids level. The other stream is a foamed phase that carries air at a controlled density. Syrup preparation begins with sugar and glucose syrup metering. Granulated sugar is screened to remove clumps and to keep dissolution predictable. Glucose syrup is held in jacketed tanks so it pumps at stable viscosity. Water is filtered and tempered because inlet temperature affects dissolving rate and cooker stability. The streams enter a dissolver where agitation produces a clear solution. Strainers remove any undissolved grains because grains concede crystallization and create a gritty center. The clear syrup then enters a continuous cooker where heat drives off water. Many systems heat under pressure, so temperature can rise quickly without boiling in the coil. After the heating zone, the syrup may enter a flash stage where pressure drops and water vapor leaves rapidly. This trims moisture to the target. Moisture control here sets final nougat resilience. Too much moisture yields a soft center that can deform under cutters. Too little moisture yields a tough center that loses its light bite. While the syrup is being cooked, the aerated phase is prepared. A protein solution is mixed to a defined concentration and then sent to a continuous aerator. Airflow and rotor speed are controlled to create small bubbles and stable foam. Foam density is monitored continuously because it is the most direct indicator of final bar lightness. The foam must be stable enough to survive contact with hot syrup. It must also be fine enough to produce a smooth bite rather than large voids. The cooked syrup is cooled slightly to a controlled blending temperature and then combined with the foam in a continuous mixer. The mixer is designed to fold the streams together rather than whip. Folding distributes syrup through the foam while preserving the bubble structure. The syrup heat partially sets the protein films around bubbles and locks in the microcell network. Chocolate flavor is built into the nougat by adding cocoa components and sometimes chocolate liquor or cocoa powders at controlled points. These additions must be dispersed without deflating the foam. They can be introduced as fine powders, pre-blended with part of the syrup, or as a liquid chocolate. Stream introduced downstream of the highest shear zone. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be added in small doses to improve stability and control viscosity. Once mixed, the aerated nougat exits as a warm plastic mass with controlled density and viscosity. It is deposited onto a moving belt as a continuous slab. A spreader head lays down the slab at a defined width. Gauge rollers and leveling bars set thickness. Thickness control is critical because it determines bar mass and also affects cooling time. The slab enters a cooling tunnel where temperature drops in stages. Staged cooling prevents a hard skin from forming over a warm interior because that skin can crack and create weak planes during cutting. As the slab cools, the bubble structure stabilizes further. Fat begins to crystallize, and the nougat transitions from plastic to firm yet compressible. The target firmness is set, so the slab can be cut cleanly without smearing. If the slab is too warm, knives drag and deform edges. If too cold, the slab can fracture at the surface and create rough edges that show through the chocolate coat. Edge trimming is often used to remove uneven slab edges. Trims are collected as controlled rework. Rework must be managed carefully because aerated material behaves differently than fresh mix. Excess rework can shift density and bubble size distribution. The main slab then moves into lane cutting. Rotary knives slice the slab into long ropes of constant width. A crosscutter then slices the ropes into bar lengths. Cutter timing is synchronized with belt speed, so each bar length is consistent. The cut centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between bars. Transfer points are designed with low drops and soft transitions because aerated centers dent easily. Some lines include a brief pre-chill to firm the surface. Firmer surfaces accept chocolate more evenly, and reduced deformation as the center passes through the curtain. Chocolate coating is prepared in a separate system where temper is the key variable. Chocolate is melted and filtered to remove unmelted particles. Tempering then creates stable seed crystals by controlled cooling and reheating. Working temperature is set so viscosity remains stable at the curtain. Viscosity controls the thickness of the coating and therefore the final chocolate to center ratio. Enrobing coats the bar with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a roller or a bath section that lays a consistent base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot at the base. Air knife settings are tuned to remove excess without exposing corners. Because the center is soft, air knife force is balanced so it does not deform the nougat under the coat. A pattern top can be applied by a stringer that drizzles thin chocolate lines over the wet surface. The drizzle must bond before the base coat fully sets. This requires a precise timing window between curtain exit and cooling tunnel entry. Pattern flow rate and nozzle spacing are synchronized with belt speed. Cooling tunnels set the chocolate. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Cooling must avoid condensation because moisture on chocolate creates sugar bloom and dullness. Tunnel humidity is controlled, and the bar exit temperature is set to support wrapping without scuffing. During cooling, the nougat center also equilibrates. The fat phase in the center continues crystallizing, and the bubble walls become more rigid. The center remains light and compressible, but it gains enough strength that handling pressure from wrappers does not deform it. The chocolate coat becomes a barrier that reduces moisture exchange and helps maintain texture over shelf life. Inspection follows cooling. Vision systems check for exposed edges and coating voids. Weight checks confirm bar mass and coating mass. Bars outside tolerance are diverted. Diverted product is handled as rework streams that are remelted for chocolate or reprocessed for nougat according to process rules. Wrapping begins once the bars reach a stable temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are controlled, so seals are tight without shrinking film onto the bar. Film tension is controlled to avoid scuffing the chocolate surface. Print registration aligns graphics to bar position. Coating adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Twix bars are manufactured by producing a crisp biscuit finger, applying a controlled caramel layer, enrobing the assembled sticks in tempered chocolate, then cooling and wrapping while moisture and viscosity remain tightly controlled. The process begins with the biscuit line because the biscuit defines the bar geometry and the snap that must survive caramel deposition and chocolate coating. Flour is sieved to remove lumps and to standardize flow. Sugar is screened so crystal size is consistent and does not tear dough during mixing. Fat is conditioned to a plastic state so it blends evenly and limits gluten development. Leavening salts are weighed precisely because they determine porosity and bite strength. Water and any dairy liquids are tempered because dough temperature controls how cleanly it sheets and cuts. Mixing is designed to create a short dough with limited gluten. Fat and sugar are first blended to distribute fat and reduce dry friction. If a creaming step is used, it is controlled to avoid excessive air because too much air weakens biscuit and increases breakage during handling. Dry ingredients are then introduced and mixed only until the dough becomes cohesive. Minimal mixing limits gluten formation and preserves a tender, crisp structure rather than a tough one. Dough conditioning follows. The dough rests so moisture equilibrates and the dough relaxes. Relaxation prevents snapback during sheeting. Dough temperature is held in a narrow range, so fat stays plastic. Warm dough smears on rollers. Cold dough cracks at edges and produces rough cutouts. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through reduction rollers that gradually thin it. Gauge rollers set final thickness tightly because thickness drives bake time and final snap. Dusting flour can be applied sparingly to prevent sticking, but excess dust is avoided because it burns and creates specks. The sheet enters rotary cutting and docking. Rotary cutters punch long biscuit fingers. Docking pins create small holes through the dough. These holes vent steam during baking and prevent blistering and warping. The cut fingers transfer to an oven band. Scrap dough around the cutouts is lifted and recycled. Scrap ratio is controlled because repeated working increases gluten and changes dough behavior. Baking occurs in a tunnel oven with staged zones. Early zones set the shape as fat melts and moisture begins to leave. Leavening gases expand and create small pores. Mid-zones drive moisture down and develop a light golden color. Later zones finish drying so the biscuit reaches a low moisture endpoint. Moisture endpoint is critical because the biscuit must remain crisp under caramel and chocolate. If moisture remains too high, the biscuit will soften and lose snap. If moisture is too low, the biscuit becomes overly brittle and breaks during sandwiching and wrapping. After baking, the biscuit fingers exit the oven and enter cooling. Cooling stabilizes structure as fats resolidify. Cooling air is controlled and often dehumidified because dry biscuits can absorb moisture from humid air. The goal is a consistent exit temperature and moisture level. The cooled fingers are then aligned into lanes for caramel application. Caramel production runs in parallel because caramel must be depositable and stable. Sugar and glucose syrup are cooked with milk components to develop caramel flavor and reach an elastic solids endpoint. The cook drives off water until the caramel will hold shape at room temperature. Fat is added to smooth the caramel and reduce tack. The endpoint is set so the caramel bites cleanly without becoming glassy. Overcooked caramel becomes hard and can fracture when the bar is bitten. Undercooked caramel flows and smears in packaging. Caramel is cooled from cook temperature to a working temperature where viscosity is stable for deposition. It is held in jacketed tanks with gentle agitation to prevent skin formation. Pipes to the depositor are heated to prevent cold plugs. Viscosity is monitored indirectly by pressure and flow because a small temperature drift changes deposit weight and layer thickness. Caramel deposition applies a continuous layer onto the biscuit fingers. A slot depositor or multi-nozzle head lays caramel onto the moving biscuit lane. A leveling bar smooths the surface and sets thickness. Thickness must be uniform because it influences bite and chocolate coverage. If caramel is too thick, it can squeeze out under chocolate and create uneven edges. If too thin, the bar loses the intended caramel to biscuit balance. The biscuit temperature at deposition is controlled. Biscuit must be cool enough to remain crisp and to avoid melting caramel into the pores too deeply. It must not be so cold that caramel fails to bond. The line targets a temperature window where caramel adheres but does not soak. After deposition, the caramel-topped fingers pass through a cooling tunnel to set the caramel surface. Cooling must be staged so the surface firms without cracking. A firm surface is required before enrobing so caramel does not smear on belts. Once the caramel is set, the sticks are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfers minimize drop height because biscuit can crack and caramel can shear. The sticks may pass through a brief pre-chill to firm surfaces and improve chocolate flow behavior. Chocolate preparation is a separate stream where temper control is essential. Chocolate is melted and filtered. It is tempered to create stable cocoa butter seed crystals. Working temperature is set to maintain consistent viscosity. Viscosity determines how thick the chocolate curtain is and how much chocolate remains after air knife trimming. Enrobing coats the sticks in chocolate. A top curtain covers the caramel and sides. A bottoming system coats the underside so the biscuit is sealed. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot thickness. Air knife settings must be tuned because too much air can expose corners, especially at biscuit edges. Too little air leaves thick feet that can crack during cooling. If a top pattern is required, it is applied immediately after the main curtain. A stringer deposits thin chocolate lines across the surface, while the base coat is still wet enough to bond. The stick then enters the cooling tunnel. Cooling sets the chocolate and locks the finished structure. The first zone sets the surface quickly to prevent slumping. Later zones cool gradually to promote stable crystal growth and reduce bloom risk. Cooling also reduces the internal temperature of caramel so it reaches its final elasticity. The exit temperature is set so the chocolate is hard enough for wrapping without scuffing. After cooling, the bars are inspected. Vision systems detect exposed biscuit corners and coating voids. Weight checks confirm portion control. Defective bars are rejected. Rework chocolate is remelted and returned upstream, while biscuit and caramel rework is handled separately because it carries moisture and texture changes. Wrapping begins with feeding bars into flow wrappers. Film is formed around each bar and sealed. Seal temperature and dwell are controlled so seals are strong without overheating the chocolate. Film tension is controlled to prevent scuffing. Print registration aligns graphics. Coding adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Kit Kat is assembled from a dry, crisp wafer core that is first strengthened and sealed by contact with a warm, fat-based filling, then coated in chocolate, then cooled so the wafer stays crunchy and the bar snaps cleanly on the finger lines. The wafer stream begins as a thin batter system that must bake into sheets with low moisture and uniform thickness. Flour is sieved to remove lumps and to stabilize hydration. Sugar and salt are weighed precisely because they affect browning and sheet brittleness. Water is tempered so batter viscosity stays consistent at the depositor. A small fat or emulsifier addition is used to control plate release and sheet texture. The batter is mixed only until smooth because excessive mixing increases gluten development and makes sheets tough and less crisp. Batter viscosity is one of the main controls because it determines how evenly the batter spreads on wafer plates. The batter is held in a feed tank with gentle agitation to prevent settling of flour fines. From there, it is pumped to wafer irons. Each iron is a pair of heated plates that close, bake, and open in a cycle. A metered dose of batter is deposited onto the plate and spreads under closing pressure. Heat drives rapid water evaporation and sets the starch matrix into a porous, brittle sheet. Bake time is tuned so the sheet dries to low moisture without scorching, because scorch creates bitter notes and weak zones. When the plates open, the wafer sheet is released and moved to cooling. Cooling stabilizes crispness and prevents warping. The sheet is then cut into finger-sized leaves. Cutting uses sharp rotary blades to avoid cracking edges. At this stage, the wafer leaves are extremely brittle and must be handled with low-impact conveyors and minimal drop heights to prevent breakage before lamination. Lamination creates the multi-layer wafer block that defines the bar bite. A thin layer of wafer creme is applied between leaves as an adhesive and moisture barrier. This creme is not the outer chocolate, but a fat-based filling designed to soak slightly into wafer pores and then set. The creme is prepared by blending sugar, cocoa components, milk powders, and fat into a smooth paste with controlled viscosity. Particle size is refined so it spreads evenly and does not feel gritty. The creme is held warm enough to flow, but not so warm that it becomes runny and floods the wafer. Assembly stacks alternating wafer leaves and cream layers. A depositor spreads cream onto a wafer leaf in a uniform film. Another leaf is placed on top, and the stack repeats until the target number of layers is reached. Alignment matters because misaligned leaves create uneven edges and weak points at the snap lines. Light compression follows stacking to ensure contact and eliminate air gaps. Compression must be controlled because excessive force crushes wafer cells and reduces crispness. After stacking, the wafer block enters a setting tunnel. This tunnel cools the block so the creme fat network crystallizes and locks the layers together. The block must become rigid enough for cutting, but not so cold that wafer becomes overly brittle and shatters. The setting profile is staged so the outer surfaces firm first and then the core equalizes. Once set, the block is cut into sticks and then into the familiar finger format. A longitudinal cutter slices the block into wide slabs. A second cutter defines the number of fingers per bar by cutting grooves or separating lanes. A cross cutter then creates bar lengths. Knife sharpness and speed are tuned to avoid crushing the wafer. Ultrasonic knives can be used in some lines to reduce drag through the cream layers and keep edges sharp. The cut wafer fingers are then routed into an enrobing sequence that is designed to seal the wafer from humidity. Chocolate or compound coating is prepared in a separate system where flow behavior must remain constant. The coating is melted and filtered. If real chocolate is used, it is tempered to create stable cocoa butter crystals so it sets with gloss and snap. If a compound coating is used, it is temperature controlled for viscosity and set rate. In either case, viscosity control is critical because it determines coating thickness and whether grooves between fingers fill correctly. Before the main enrobe, many lines apply an undercoat or pre-coat that improves sealing. A thin coat can be applied to the bottom first to reduce moisture migration from the environment into the wafer. The bars then pass through a curtain that coats the top and sides. Excess drains through a wire belt. Air knives remove excess and shape the surface. Air knife settings are tuned to avoid stripping too much coating from corners because exposed wafer edges absorb moisture quickly and lose crispness. If the bar is intended to have fully defined finger lines, the coating flow must not bridge the grooves excessively. Groove definition is managed by coating viscosity, curtain temperature, and belt speed. Too thin a coating leaves exposed edges. Too thick a coating floods grooves and reduces snap separation. The process targets a thickness that seals the wafer while still preserving the break lines. After coating, the bars enter a cooling tunnel. Cooling is staged to set the surface quickly so it does not slump, then to crystallize the full thickness without stress. Stable crystallization prevents bloom and keeps the surface firm for wrapping. Tunnel humidity is controlled to prevent condensation because moisture on the surface can cause haze and can also migrate into wafer through microcracks before the coating fully sets. During cooling, the wafer core is also protected from moisture changes. The internal creme acts as a barrier and binds wafer layers, but the wafer will still soften if the coating does not seal fully. The combination of internal creme saturation and external coating seal is what maintains the distinctive, crisp bite. A properly set bar has a rigid, layered core that fractures sharply and a coating that